Okay, here we go with lesson 4. It's I emphasise, an optional lesson, but I would say that question 1 is kind of good for everybody. So there's no exercise associated, but you'll see question 3 is definitely like an exercise. So here we go. Question 1. Now make sure you try this yourself before watching this. So we have dy dx equals negative x on y. Separate those. Y dy equals negative x dx. Integrate. Get these primitives, they're pretty easy ones. Equals negative half x squared plus c. Okay, I'm going to double to get rid of the halves, but I'm not doubling the c because it's still just a constant. And quick rearrangement, x squared plus y squared equals c. How awesome is that? It's a circle. All right, so a nice simple differential equation has given us a familiar shape of a circle. Now we've got information here passing through 3, 1. So if we sub 3, 1, well, that can be done mentally very easily. C equals 10. And so we have x squared plus y squared equals 10. All right, a couple of comments here. Just going to try and get a couple of straight lines going and see how I go with a circle. Pretty good, not bad. Right, so here we have a point 3, 1. The circle itself has a radius of root 10. But what else can we observe? Well, this is a differential equation. So let's look at the gradients. Here they're negative, positive, negative, and positive. Right, I've looked at the 4 quadrants. So quadrant 1, 2, 3, and 4. We can look at x and y, and then we can look at y dash is negative x on y. So in quadrant 1, x, we've got positive and positive. We've got negative, positive, negative, negative, and positive. Oops, I rushed that. Positive and negative. And if we calculate negative x over y, then in the first quadrant we've got negative positive over negative, negative positive over positive. That makes negative, and then that's positive, and negative, negative, negative makes negative, and that makes positive. Okay, and that agrees nicely with first quadrant negative, second quadrant positive, third quadrant negative, fourth quadrant positive, as we've got here. So just showing a little sanity check on what we've found. Next thing to comment on here is y dash equals negative x over y. So as x approaches 0, y dash approaches 0 because x is in the denominator. And as y approaches 0, then y dash, y is in the, I said denominator before, x is in the numerator. Y is in the denominator, and so as the denominator approaches 0, we get a very steep gradient, plus or minus infinity. And we can see these are the 2 points on the circle where y is 0, and they have a vertical gradient. The 2 points on the circle where x is 0, they have a 0 gradient. And as the curve approaches that, the gradient is approaching 0. As the curve approaches here, then the gradient is approaching infinity. Okay, so that's it for question 1. This was accessible to everybody. question 2 is where we get into something that's really just for interest. It helps us to get a broader picture of what we've just done. Okay, I think I'll stick with purple pen just for fun. So if we can solve y dash equals negative x over y to get x squared plus y squared equals c, then surely we can differentiate x squared plus y squared equals c to get this. All right? If basically we integrated this, we didn't just integrate, of course, but integration was heavily involved, but we solved a differential equation, so we should be able to differentiate this to get that. But how? Well, there's something called implicit differentiation, which is not in the course, but it's not hard to learn, and I think it's good for you. If we can get from there to there, then really, but nice to understand how to get from here to here. Okay, so we start with x squared plus y squared equals c, and now we're going to differentiate both sides with respect to x. Term by term. 2x, not sure. Derivative of c with respect to x is 0. Right. We'll come back to this, but here's this aside, and it's a little bit squashy, so I'm giving myself lots of room. Okay, y is a function of x. So what's the derivative of y with respect to x? That's really simple. That's dy dx. And, or y dash. And just to make life a bit easier, in this table I'm going to write y dash instead. Okay, what's the derivative of y to the power of 4? Well, we've got a function of x to the power of 4. Right? If y was, say, 2x minus 3 to the power of 4, then to differentiate that, okay, we're using the chain rule, aren't we? Well, here, so if we've got y to the 4, then if I do the same thing, then that's 4y cubed times y dash. Okay, it's 4y cubed times the derivative of the inner function, and the inner function is y, and the derivative of that is y dash. So this is the skill related to implicit differentiation. Okay, continuing a little more quickly. So y cubed, we have 3y squared y dash. Y squared, we have 2y to the power of 1 y dash. We're going to need that in a minute. Log of y, 1 on y times y dash, which is very similar, well, really identical to something that you know well, and that result comes from the chain rule. This is just using the chain rule. Sine of y, cos of y times y dash. All right, change colour because we're doing something a bit different now. xy needs the product rule, because it's a function times a function. These all need the product rule, and this one needs the quotient rule. So xy, we've got the, oops, sorry about that. Okay, there's our u, there's our v. Right, we've got y times 1 plus x times y dash. X squared y times 2x plus x squared times y dash. dy dx is clearer because there are powers floating around here, but don't have much room. So xy squared, oops, got y squared times 1 plus x times, now what's the derivative of y squared? 2y times y dash, oops, times y dash. And that would, this would simplify to y squared plus 2xy y dash, okay? you could simplify any of these. And then finally, y over x, we've got our, right, so it's vu dash, so there's our, so it's x y dash minus y times 1 over x squared. Okay, so this, using the product rule, quotient rule and chain rule is important when we're doing this kind of differentiation where our x's and our y's are mixed up and can't really be separated. Now, the reason it's called implicit differentiation is because this is an implicit function. I mean, it's not even a function, but it's an implicit relation because neither x nor y is a subject. It's all bunched up together. And so that's why it's called implicit differentiation. And so back to what we were doing before, all right, the derivative of y squared with respect to x is 2y times y dash. And so if I just rewrite that nicely, 2x plus 2y times y dash equals 0. And now make y dash the subject. So 2y y dash is negative 2x y dash. Okay, so we completed the circle. We have gone that way, and earlier we were able to go that way. And I think that's very important, even though it's not in the syllabus. Right, compare the above with a conventional differentiation. So if we start with x squared plus y squared equals c, if we make y the subject, we would have a plus or minus. I'm just going to take the semicircle here. That's c minus x squared to the power of a half, and continue. So y dash, right, using the chain rule, so half c minus x squared to the negative half times the derivative of the inside, so negative 2x, and that's half of, so if we get the rest of it, we've got negative 2x over c minus x squared to the half. Now, say no more. Right, so we were able to get y dash equals negative x over y from this without doing implicit differentiation, but we only did it for a semicircle, not for a full circle, and it was a messier process. So normally we'd kind of, if you're just doing a year 11 calculus question and you say, find, the question might be y equals the square root of 7 minus x squared, find the derivative. You're going to get something that's, not very neat. Like they'll cancel and you'll get something like this. Negative x over square root 7 minus x squared. Okay, and you're going to leave it there because we're conditioned to thinking in terms of x. But in this topic of differential equations, we are comfortable with thinking of the derivative in terms of x and y. And when we have if we have a relation as opposed to a function, then the derivative needs to be in terms of x and y, because if you pick an x value, there's not just one point on the graph that has that x value, and of course they have entirely different gradients. So the gradient needs to depend on x and y. Okay, question 3 is really just a power exercise to practice the implicit differentiation, and it's a bit of fun because these curves are pretty cool and you can graph them. I haven't tried every single one of them, but all the ones I have tried look very interesting, and the software can handle them. I use GeoGebra, but maybe Desmos would work as well. I will do A and B, and then I'll leave the rest to you. I won't be providing answers, at least at first, because I believe that Wolfram Alpha would work for you. So let's say you did this and you got an answer. Then to check your answer, I'm sure you could type this into Wolfram Alpha for cos x sine y, brackets just help it to be unambiguous. And now you could probably leave it there, but I reckon it would understand that. WRT with respect to is understood by mathematicians everywhere, and I'm sure it would be understood by Wolfram Alpha. If you are unable to get answers that way, then you can ask me and I'll do something to provide you with answers to these. Okay, if I do question A and B like I promised. So we have x cubed plus y cubed equals 6xy, and we're interested in the point 3, 3. Now, differentiating this with respect to x, we get 3x squared plus 3y squared dy dx. Like I said, dy dx looks nicer than y dash when there are powers everywhere. I'm going to take out the 6 and do the product rule on x, y. So we get y times 1 plus x times dy dx. There's a factor of 3 on the left side, a factor of 6 on the right, so I'll simplify that. X squared plus y squared dy dx. And I'll expand, so I've got 2y plus 2x dy dx. And oh, that's right, we've got a point here. So if I change pen, if I sub 3, 3, then I get 3 squared plus 3 squared. I'll just do y dash 2 lots of 3 plus 2 lots of 3 y dash. Now, I don't even want to continue really, but right, 9 plus 9y dash equals 6 plus 6y dash. 9y dash plus 6y dash equals 6 plus 3y dash equals negative 3. Y dash equals negative 1. Okay, and that's true. So I phrased the question this way just to show that you don't have to tidy this line up before you substitute. If you are really looking just for a number, a numerical gradient, you can substitute here and do your work. Okay, but there's something a little, I don't do that naturally, there's something a little unsatisfying about that. So now we'll get into finding the general gradient here. So it's just about making dy dx a subject, and all I have to do is just put the dy dx on one side and factorise out. I've got y squared of them and I need to subtract 2x of them, and the other bits are 2y minus x squared. So dy dx 2y minus x squared over y squared minus 2x. Right, so that's solved in general. Question C was to graph it. It's a pretty cool graph. Looks something like this. And it's got a sort of kind of extreme point here of 3, 3. That's why I chose that point. It's the only integer point I could find on the, and that has a gradient of negative 1 as we found. Okay, but you could find the gradient anywhere, but you need both the x and the y value. Look how non-functional this is. That really fails the vertical line test, doesn't it? Okay, there's no more. So, yep, like I say, if you have trouble getting answers to these to check, then just let me know. Okay, farewell.